everyone. The first talk of the afternoon session will be Annette Werner speaking on the p-adic Simpson correspondence for torsors under commutative rigid groups.
Yeah, thank you very much, and thanks for the opportunity to speak here. This is a great pleasure. I'm reporting on joint work with Heuer from Frankfurt in Mingjia's Zhang. Mingjia is here in the audience. And before I want to explain you what we did in the p-adic world for torsors on the commutative groups, let me briefly recall the classical Simpson correspondence and the particular statement which we want to generalize from this correspondence. So we start with a brief recollection of the Archimedean situation before we do the p-adic version. And the result I want to recall here is the result for linear algebraic groups over the complex numbers on complex scalar manifolds, namely, as I call it, Simpson correspondence for G-Higgs bundles. Simpson. Sometimes I abbreviate this by CS. Is following. There is an equivalence of categories between homomorphisms of the topological fundamental group to our algebraic group and the category of, I need more room, semi-stable G-Higgs torsors, stable G-Higgs, let's say G-Higgs bundles with vanishing true classes. So our group can be GLN, SLN, orthogonal group, or something like this, some classical linear algebraic groups. This is obvious. We're looking about homomorphisms from the topological fundamental group, for example, representations on finite dimensional C vector spaces. The category of Higgs bundles is the following. We will need an analog in the p-adic world in a second, so let me write it down. You have a pair, bundle and Higgs field, and the bundle here is the G torsor on X holomorphically. For example, if G is GLN, we just have a vector bundle on the X, and the Higgs field is a global section in the adjoint bundle tensor omega, with the property that when you push it to omega 2, it vanishes. So this adjoint bundle you get by converting the G torsor into a torsor under the Lie algebra by the adjoint action. So this is the endomorphisms if you are working with G equal to GLN. Okay, now this is nicely written. I hope you can read the sideboards, please, otherwise complain, then I will move it up a little bit. Okay, and of course, I'm formulating it here for general groups, but the main effort is, of course, the case G equal GLN. This requires a lot of work first, and then you deduce the other linear algebraic group cases by suitable Tanakian arguments. Use connected arguments. By reducing everything to factors on some representation category. The very definition of semi-stability here in vanishing Chern classes is through all representations of G. So all homomorphisms from G to GLN, if the resulting bundles are all semi-stable and if vanishing Chern classes, then you say that the G-Higgs bundle has this property. Okay, Good. So the first thing we want to do is get such a result for linear algebraic groups in the p-adic situation, and then discover that p-adically we can take a completely different kinds of groups also to get nice solutions. So now let's move to the p-adic situation. This was two p-adic situations. And this will mean we are working in a geometric situation over a field, complete, algebraically closed and containing P. And over a proper rigid space, smooth, proper smooth. So we are very happy if we can do anything for proper smooth spaces, so we'll always assume this, rigid spaces. And by a rigid space, I will use notation a little bit, so sometimes I have rigid, sometimes adic, sometimes Berkovich, but things are always nice. So to be precise, rigid means we have a nice adic space, K, which is quasi separated and locally, topologically of finite type. So this is what I mean by rigid, yeah? So I don't care so much in which category we work. And this abuse of the same notation for all categories gets worse because we don't hesitate to denote by X also the diamond associated to X. So this is an even more fancy category in which you can faithfully embed such smooth rigid spaces. And I will not distinguish notation. X denotes also the associated diamonds. Sometimes we need this to work with topologies which are not defined in the rigid analytic world, but in the world of diamonds. It's not necessary that you know what that is. If you are happy to accept that it's a category which allows for more general constructions, and believe me that the constructions I write down make sense in this category, this is enough, I hope. Okay, in this situation, let's start with the same groups as over here. We take a linear algebraic group and we take its analytification. For example, GN analytic or GM or GA or GLN. As a linear algebraic group over K. So then you have the following analog of the theorem in a special situation. So this is in our preprint. You might call that this is a p-adic, call it Simpson correspondence, but for linear algebra groups, but I need a special X. Maybe I need for this theorem X to be an abelian. I will say something more about this choice in a second. First, let me write down. So we take an abelian variety. So abelians are the rigid analytic cousins of abelian varieties. Every abelian variety over K gives you such a guy, but since these are connected, smooth, proper, commutative group varieties, you might find rigid analytic ones which are proper but not projective, which do not come from the algebraic world. Variety. Connected, smooth, proper, commutative, rigid group variety over. If you're not familiar with this, just take any abelian variety and analytify it. Okay, and now we need something which one might call the universal profinite étale cover of this thing. And here I need to work in this more general theory where in these limits, like this one, take the limit of all n multiplication map exist as an object. This is in this case even a perfectoid space, but in particular it's a diamond. And we might call this for good reasons, because you here basically have all the finite detail covers, the universal profinite detail covering. Yeah. This is a nice space mapping to A, and it's in fact a torso under the Tate module. So then in this situation, we have an equivalence of categories. So here we have something on the homomorphism side, and now we have a topological group replacing the fundamental group, namely the étale fundamental group. I take the base point 0, so it's the Tate module. So we have to work with continuous homomorphisms. And on the right-hand side, we have the G-Higgs bundles. Theta. This time I take the étale topology to define E, such that the bundle of the torsor itself becomes trivial after pullback to the profinite étale cover. So here, this is a similar definition as the definition over there. So E is a G torsor for the étale topology. Theta is defined in the same way as it is defined here, same definition, but the condition is a little different. Yeah? I do no longer work with this semi-stability with vanishing term classes, and one knows from results by Heuer in the case of line bundles that this would, even in the case G equal to GM, not hold an equivalent where I just use this very definition would not be true even in the rank 1 case. We need something a little more restrictive. And in this case, the more restrictive thing is, but this is definitely a special feature of abelian commutative situations, is that if you take this G torsor and you pull it back over here, it becomes the trivial G torsor. Okay, so and the proof of this fact, of course, you do GLN first, and this was done in a joint paper together with Ben and Lucas. So this was Werner and Lucas Mann, who is here. And then in this preprint with Ben and Mingjia, we show how you can adapt Tenekian arguments from Scholze-Weinstein's book to this situation to deduce this case. Use Tenekian. This was fun, but not so very surprising that this worked. Yeah? Okay. So now, why do we work in such a restricted situation? So we are not working. Possible proper smooth rigid space. We are working in this abelian space. I mean, and the reason is we don't have a general theory, even for GLN, beyond that case. So we cannot, we cannot use the Tenekian machinery if we don't even know what's happening for vector bundles. So why abelians? Yeah, well, for G, note for G equal GLN beyond the line bundle case. So the line bundle case is done in general on any smooth proper X by Ben Heuer, but beyond this case, for general smooth proper, we do not have a p-adic Simpson correspondence yet. So there's also no need, no angle point to generalize this to linear algebraic groups. So this is still a difficult thing, which is open. However, funnily, in the p-adic world, there exists in this general situation a correspondence which is more general than the classical one, yeah, which sometimes is called the generalized Simpson correspondence. Simpson correspondence. And this was established first by Faltings on Heuer for G equal to GLN. Vector bundles, which is the most difficult case on curves, and by Heuer in general, and also in this rigid analytic situation without any assumption about toroidal models and so on. And this says the following: you have a space like this with smooth proper rigid. If I forget this, it's always X has always the same attribute. Rigid. Okay. G is the analytification of a linear algebra, right group. And then we have an equivalence. It is even exact equivalence where, yeah, now we are doing something much more general. The representations or the group homomorphisms will have to go, but instead we talk about G-Torsors on the diamond associated to X with its very general V topology and G-Higgs bundles on X. So this is just Torsors under G for much more general topology. And this is the category of G-Torsors on the étale side over A, together with the Higgs field, no condition. Yeah, so no pullback condition, no semi-stability, nothing, all these bundles. And of course, this is something, so here the category is much more general, there the category is much more general. Why generalized Simpson? Well, you can prove for G equal to GLN, one can show that the left-hand side is actually in modern terms, so in modern language, is what Faltings calls the generalized representations in his original paper. So the left-hand side corresponds to Faltings' notion of generalized representation. Because if you look into the paper, I mean, these notions didn't exist, so you had to define it differently, more from scratch. But if you look at this paper on curves, you can translate the left-hand category, generalizes the representation category as the category of G-Torsors for the V topology on X. Okay, so this thing really exists for analytifications of linear algebraic groups on any smooth proper variety. And in this generality, it is to Heuer a tiny epsilon, namely the generalization from G Ln to G is in our joint paper, but the main work by far is the GLN case, which is in Ben's paper. Okay. It is not clear, however, how to restrict this. I mean, you can embed the continuous homomorphisms in this category. We will do this in a different setting later on. But at the moment, it is not clear what category would correspond to that subcategory here on the left-hand side if you move to the right. This is open. Okay, so it seems we are kind of stuck here. This case exists, and in the other case, we don't know what to do beyond evaluate varieties. Yeah, but if you don't know how to prove something, sometimes it's a good idea to generalize it. And even if some very clever people manage to prove the generalized theorem, but some not so clever people find other special cases of the generalized theorem, which they then can prove. And this is what we are going to do here now.
Wait, sorry, can I?
Yeah, please, Bader.
So in this second theorem, this is the one where there are some choices involved, right?
Yes. I knew that. Too many people in our learning seminar.
Okay. No, the question was, did the first theorem also use those choices?
Yes. I should say, and you will see the choices on the blackboard in a second. I should say, depending on some choices, so we will have the same choices later on when I write down some more theorems here also, choices. And everybody in the learning seminar will know what they are, because we've had them on the blackboard.
You said for people who are not.
I will, but later on. I will later.
I could not really follow the discussion. So the first theorem is subject to some choice. What else?
I can say it. I can say it. So you have to choose a splitting of the Hodge filtration, and you have to choose a splitting of the logarithm.
Of the
Logarithm map of the theorem.
oh, but the second one is more or less canonical. p-adic.
Yeah, p-adically you have to choose something when you extend it. Let me do this a little bit later on, I mean in more details, because I hope I come to the proof of the theorem I still have to state, and then we see where these choices actually go into the construction. So but thanks, there are some choices involved which are really kind of inherent to this p-adic situation. Same here. I should maybe add that. Don't forget choices if you want to know exactly what it is in the literature. Okay, so how about the generalization which I was talking about? The generalization concerns the group. Now I will just work. Why not? Now let G be any rigid analytic group. Not just groups coming from linear groups over in the algebraic world, but any rigid analytic group. Group, of course, is the group object in my category of rigid analytic varieties. When I talk about rigid analytic group, I always mean such a thing. And okay, we can try to formulate these kinds of results for any rigid analytic group. For example, I mean, you could take an abelian variety, yeah? If you remove the condition that it's linear algebraic, you could take very basic stuff, which is just not
Rigid analytic groups always come as the generic fibers of group objects in formal schemes.
No, only, I mean, I think I would call those with good reduction. And I think every such guy has an open subgroup which comes along as this in the way you are describing, but not everybody does. Okay. So goal, how do we generalize it? We are looking for pairs X, G. So X is as usual my smooth proper rigid space over K. G is the group object of these rigid spaces over K, such that we have an equivalence between, so this is an equivalent of, call it, continuous homomorphisms. You can't read, Ellen, can you read that?
Not really, but.
So my test object, can you?
That's all right.
Can you read that?
Yeah.
Can you read continuous? Okay, then, so this is the forbidden zone. Continuous homomorphisms from the Italian fundamental group to G, replacing GL. Yeah, and then we just copy the definition of Higgs bundles. There's nothing in it which needs that G is linear algebraic. So G Higgs bundles. On X et al. Yeah, but if we are really talking about honest representations, we need a condition. And the condition is difficult. So I will just be vague and satisfying some condition. Yeah. It is at the moment not even contractually clear what this should be in all generality, and only we have several examples. And this is also a good case, a good point for why you should study specific classes of examples. If you do not even know what the theorem is you're trying to prove, it's a very good idea to study specific cases first. This condition on abelian varieties would be triviality after pullback to the universal to finite covering. So this would be a call it Simpson type correspondence, or the generalized type of correspondence. So this is one between all G torsors on X for the V topology, and also explain later on how you get from here to there. And you have any G bundles. No condition.
Sorry.
Yes.
Even in the Corlett-Simpson case, if X is abelian, is it clear that the condition is supposed to be the same one as you have written down, even if G is not Hilbert?
At least conjecturally. I mean, is it clear? We can even, so I will show you in a minute that this is false for general G, whatever X you put in. So we have to be a little careful. If you have nice G, I think the condition is that. But we will see in a minute that you cannot expect this to be true for any G, so you need conditions on G. Okay, so we have now, so far, we have seen that this holds. The first one holds, so this is a generalized Simpson case. We have seen that the first one holds if X is an abelian variety, and this condition is, and this G is a linear algebraic group being pushed to the analytic world. And we have seen that this holds on general X for linear algebraic groups. Okay. We want something for any stupid rigid analytic group. We have to be a little careful because we have to be a little careful with conditions. Look at the following example. So let's first do the very simple. So let's look at the two groups, closed unit ball, very simple groups. I call this closed unit ball GA plus because for me it comes from O plus in a certain way, but it's just the unit ball in GA, and I will not write, so by GA, I mean you take the algebraic group GA and analytify it by, I will only work in the rigid category, so please allow me that I not put an everywhere. Okay, let's look at those two candidates for G. I mean, we know that the thing works because this is linear algebraic. This is not covered yet because this is not the analytification of anything algebraic, yeah? Okay. So if G is GA, theory is much older than ours. So it was already previously known by Scholz's p-adic theory. So because Scholz's p-adic theory on rigid variety gives us a Hodge-Tate sequence. I should go on with the forbidden zone, I guess. So here, Hodge-Tate sequence. 0 goes to étal homology, and now I'm not writing structure sheaf, but for consistency, since I work with group, I write GA. Continues pi1 into, yeah, I'm not writing K, but GA of K, and H0 X omega 1. Make the arrows move. Twist. Yeah, and this is surjective. This has to go over here. Okay. So this is the Hodge-Tate sequence, which you can prove in this way by pushing forward the structure sheaf from the pro-étal side to the étal side on X. And if you look at this with the point of view we are taking here, I mean, if you look at this from the point of view of Higgs bundles, I mean, you see that when you choose a splitting, so here we choose a splitting of this Hodge-Tate sequence as vector spaces, yeah, then you see that the homomorphisms, the continuum homomorphisms here correspond to the datum of an étal GA torsor on X, and this will be a Higgs field on that. Because if you do the adjoint bundle, it will just be, I mean, the adjoint representation is trivial, so you are just of the Lie algebra left, yeah, so to speak, GA left. So this already will prove that you have, they call it Simpson correspondence for this group. I mean, of course, this is only a statement about isomorphism classes, but it's not hard to upgrade this to something about individual objects. Yeah? Okay. So this already gives us, they call it Simpson correspondence for GA. And you can go on, because this here, by primitive comparison, this is just the V homology H1V for the group GA by primitive comparison. This is, maybe it looks more familiar if I write Broital, it's the same thing. So it's a Broital homology by primitive comparison, and this is the same as the V topology. And so you see that you can also identify the class of a V GA torsor on X with the same splitting with the class of an Ital torsor and a Higgs field. So in the same sequence gives you also a generalized, so this gives you CS and generalized Simpson for the group GA. They just coincide. So we see we have to be a little careful with the definitions. Yeah? But so in this situation, both coincide, both are true, and both have been proven by Schwarze. Okay, okay, this is really, really nice. But what about that group? If you are looking at this unit ball, you can play the same game. Yeah, start with an integral version, write down an integral version of the Hodge-Tate sequence, and then if you do this, you can start with the homology of this GA plus, then you go on to the continuous homomorphisms from pi1, okay, into GA plus, okay, you go on to the field side, but now you have a problem. This is not going to be surjective. This is the same object here and there, yeah, and you definitely have less integral homomorphisms than homomorphisms at all. So this is not surjective. So there is no way that you can get any kind of these correspondences for the group GA plus, yeah? Because you will not find, even if you choose splittings and something, you will not find anything involving all the Higgs fields, for example, on the trivial band. So GA plus will not work. Okay, we have to be a little careful, we see, with the choice of groups, yeah? Okay, so now when we try to look for these groups, we will need a condition. This will be my next task. I want to explain to you what kind of condition I need. But let me first clean the board. Any questions so far?
Question?
Yeah, please.
Say something about Falking's generalized representations. What are they?
This is, if you want to formulate what the Provital topology is without having it, and you have to talk about certain systems of objects modulo all p to the n fitting together, then you would come up with this definition. So I want to write it down, but I can't really remember it fully, but it is. Yes, somehow he was aware of a good theory before we had a formal way of dealing with it, and just worked with objects which might look a little ad hoc because you had these sequences. But if you, I think if you really want to go into detail, it would be good to read one of the papers where people actually show that these can be now read as the V as Torsors for the V side. If you need a reference, let me know. Okay. So what kind of conditions do we need? And it turns out, yeah, if you look at what Ben has done in the case of line bundles, so for the big GM, one knows that the logarithm map always plays an important role. So you need groups which have a good logarithm map. And these groups were fortunately investigated previously by Laurent Farc, and we need a condition which is called a locally divisible, p-divisible group. And let me write down what this is. So that's my next chapter, locally p-divisible group. The only thing you know so far that this will be a condition which kicks this evil guy out, yeah, the GA plus. Okay. So from now on, I will always assume that G is commutative rigid group. This is, of course, a big instruction. But even here we see that things are far from obvious, and one really has to read through the forest of examples to see what could be true. So Farc defines an analytic p-divisible group. Let me repeat his definition. So an analytic, rigid analytic, p-divisible rigid group is a commutative rigid group, so a commutative group objects in the world of rigid spaces. Commutative group such that the group is topologically p-torsion. This can be expressed namely in the most simple way that all points in the associated Berkovich space have the property that if we raise them to the p to the nth power, or here I write it additively, if we take p to the n times x, that this goes to 0. Yeah, so topologically, they are p-torsion. And p-divisibility means the p multiplication map on x is a finite and surjective.
What is the upper index on the G here on number 1?
This is the points in the Berkovich space.
Oh, Berkovich.
You can define this also more fancy with V-sheaves, but I hope that this is so. In some enriched topology, you have this simple condition for points. Yeah, good. So this is we need a slide. We need a little bit more general. We need something a little bit more general because many groups we are interested in, for example, GM, are not topologically p-torsion. Yeah, but we can. So this is one, but we can work with groups, commutative rigid groups, which are locally of that type. Commutative rigid group G is locally p-divisible. If we have an open rigid subgroup, which is p-divisible itself, and rigid such that H is an analytic p-divisible group in Farc's sense. Analytic p-divisible in the sense of 1. Yeah, examples. So GA is locally p-divisible and GM is locally p-divisible. Here, here topological torsion is no problem. Here I have to go to the subset. I will write it like this. So this is the group which reduces to 1. These guys, so this is a topologically p-torsion subgroup in this group, yeah, which has the property that the p multiplication is finite and surjective. So these are nice, and also abelian varieties are, in the sense of 2, locally p-divisible.
This condition is satisfied. How many candidates are there for H?
Yeah, I think you can, you could make it smaller, I guess, yeah. I mean, you can, there is typically a largest one. So you can define for any rigid analytic group, you can define its p topological subgroup. So p topologically torsion subgroup, which is the maximal p topologically torsion subgroup, and you can prove that this condition is fulfilled on any stupid H if it's fulfilled on the biggest candidate for a p topologically torsion subgroup. Yeah. So normally you are not worrying about the smaller ones. Yeah. Does that answer your question? Okay. Where was I? Here. Example, GA, GM, abelian varieties are locally p-divisible, but of course, the bad guy is not. Yeah. If you have something which has absolute value or equal, lower or equal to 1, you will not be able to divide by p. Okay. Okay, and what we need also from Fark's theory is the logarithm map he describes and describes. So if G is locally, is an analytic p-divisible, we have to analytic p-divisible in a sense, then we construct a logarithm map. This is the map between rigid varieties. So if I'm talking here about the Lie algebra, I have to soup this up into a vector group so that I have a rigid analytic space. So he constructs this logarithm map, which is surjective, and the kernel of this thing is something which looks more like a p-divisible group, because the kernel is this whole limit of p to the n power elements. So this is a little bit more structure, yeah, than you would maybe naively think when you hear p-divisible groups. Okay, good. And now let's see what we can do for locally p-divisible rigid groups. For theorem, room 1. Okay. So this works on any, let me maybe for security we will assume connected smooth proper rigid space. And G is a locally p-divisible group. P-divisible analytic group. Then choices of an exponential map for K. For K. So this would be a map field 1 plus the maximal ideal. And an exponential map is just something splitting the logarithm map, which you can define by its usual series. Splitting the map. Okay. And so this is one choice, and choices of an exponent of a splitting of the Hodge-Tate sequence, which is here. Hodge-Tate. induce an equivalence of categories of this generalized Simpson flavor, namely relating G-Torsors on X for the V topology to G-Higgs boundaries on X entire. So in this case, any smooth proper rigid space, and here a commutative group satisfying a, which example shows necessary p-divisibility condition, then if you choose those data, you can get an equivalence of this type here, of the general kind. Okay. If I have time in the end to say something about the proofs, we will see how in the construction of this equivalence these two data enter. Okay, but before I do this, okay, let's try to do the story, which is always a little harder, namely to say something about the representation side. So something of, let's call it Simpson flavor. Yeah. What can we say about the continuous homomorphisms from the entire fundamental group to G? Okay. So first of all, so what about representations or maps from the entire fundamental group to G? Yeah, first of all, whenever you have a continuous homomorphism row like this, so let me say continuous. So this is something which would sit here on the left, in this upper correspondence. Yeah. How do you get? There's a very easy way of going from such a representation to a G-torsor. You could just take row and push out the one entire x to the x torsor x tilde over x. So here we need the same construction as previously on abelian variety. Once you are willing to work diamonds, you can form limits of all finite étale pointed coverings. So connected finite étale can form the limit of all those guys. So you have some kind of universal profinite extension as a diamond. It's not, I don't know if this is, I don't know exactly when this is perfectoid, only for, I think for curves and for abelian varieties, we know it. In general, I don't. But it's a nice diamond space. And you can prove that this is a torsor over X for this regarded as a V-sheaf in the V topology. So then you can push out, once you are in this very general framework of diamonds in V topology, you can just take this torsor, you have a homomorphism here, you take the push out and you get G-torsor on our X. Okay, so the way of going from the categories on the left-hand side from top to bottom is quite clear. The question is always what do you get on the right-hand side. So we get a functor, hence we have a functor. Hence we get a functor. From the continuous homes of the fundamental group. Okay, I push out to this to these G-torsors on XV, and then we go on to the G-exponents. No, I will not do this. I will just go to the G-torsors on the V topology, and precisely we will land in G-torsors which are trivial after pull back to the X tildes. This is, of course, a condition. I mean, if you push out, you will get something trivial when you pull back. And hence we can go here to the right-hand side, and the question is triviality on the universal profinite eternal cover. What does that mean here for this one? Okay. But life is even harder at that point because this functor f, if you are in a situation where the group is not coming from a linear algebraic group, does not always behave well. The first thing you encounter is that it is surprisingly, yes, Ellen.
On the right-hand side, there is no Higgs here.
There is no Higgs here. No, it's no wonder that you're confused because I changed my mind. We are just going from here to there.
To here.
Okay.
Okay. But you are not going to tell us what they correspond to?
Oh yeah, I will.
Okay.
But only after I tell you. But only after I tell you why I need such an additional assumption, because it doesn't work in general. Okay, it's not that easy. I mean, let me tell you why. I mean, you have this functor. Okay. First of all, it is really, if quite some work to show that this functor is essentially surjective. So whenever you have a torsor for the V topology, which is trivial on the universal profinite cover, okay, you can play your game by looking at the descent data you get for this thing, yeah? But then you realize that everything is perturbed if the group, if this is not G of K. So if this is bigger than G of K, yeah? If G is a linear algebraic group, you will have no global sections here on that, but this is not true in general. So these things, you will suddenly get cohomology classes under this group, and you want cohomology classes under this group. So you have to work quite hard to show that this is actually the same. So these are not the same, but the cohomology will be the same. So, okay, so this is work, rather technical work, but it can be done. It needs really some input in order to do this. I mean, you have to write down a map between two continuous cohomology groups. So one is with this coefficient, one is with this coefficient, G is commutative, so this will work. And then you really have to look at the obstruction. The obstruction is something which are pointed maps from X tilde to G. And then we have to prove some with some rigidity lemma that whenever you go from a proper rigid space to a smooth rigid group, it factors through an abelian subvariety. So, and then we work on abelian subvariety. So this is some work, but in the end it can be done. Okay, and then you think, oh, that's fine. Now I will at least here have an equivalence of category, which is really very easy in the case where G is a linear algebraic group. But no, I mean, we open the door to another class of examples, non-linear algebraic groups, but analytifications of abelian varieties, and they can be nasty. So you can now look at stuff like take an abelian variety and look at the A torsors over A for the V topology. Yeah, you can play games like this. Okay, and you might encounter the following problem. Take two abelian varieties. So X is the analytification of an abelian variety and G is the analytification of an abelian variety. Both is allowed. So both are simple abelian variety, and as always, I don't write analytification if I go from algebraic to rigid analytic. Abelian varieties with good reduction. I mean, what could be better? Good reduction, which are not isogenous. But such that their reductions, I mean, you have an abelian schema, and the reductions are abelian varieties and positive characteristic, and you assume that the reductions are isogenous. Yeah, and now you can do the following. I mean, if you analyze this universal profinite étale extension, you find that isogeny of reductions for abelian varieties with good reductions leads to an isomorphism between the universal profinite étale covers. Okay, Hence, we can write down something very stupid. We take our tape module. It sits in the universal cover. This is the same as B, and then we go to B. Okay, now we have, this is X, this is G. We have something from the fundamental group of X to the k-rational points of G. Continuous sits in here, yeah? Okay. But the problem, if you push, this is a non-trivial homomorphism because you don't have anything from TA to TB because they are non-isogeny. This is non-trivial, but if you do this push-out construction, the push-out will of course be trivial because it goes over the cover, but f of rho is trivial. Okay, so this can happen, yeah? I mean, you have these things to take into account. I mean, it's always the case, whenever you go from p-tensors to representations, there's always something, something going on. And even in this basic case, there's something going on because you lose information here, yeah? You cannot do that. Okay, so we cannot hope if we cannot identify these representations with a subcategory here, we will also not be able to identify them with a subcategory of Higgs bundles. Okay, so I mean, this just won't work. In this case, we will not get a pair GX as above. Yeah, but luckily we can get rid of this under the condition that all these guys are constant. Then stuff like this cannot appear. Funny, funny things, funny maps between A tilde and G as they are here cannot appear, and then it works. So that's theorem 3. G and X has in theorem 1. So G is X is any proper smooth thing. G is this locally p-divisible rigid group. It's here. And if all morphisms from the universal for finite eternal cover of X to G are constant, then the equivalence, you have to make the same choices, then the equivalence of theorem 1 restricts the equivalence of categories which has this called Simpson flavor. We take continuous homomorphisms from the eternal fundamental group on the one side to G of K. And if you don't allow funny maps here, the functor will be in fact fully faithful. You can embed it here. And what you find on the right hand side, this is the category of G bundles, E theta on X et al, such that the bundle will be trivial on the universal profinite et al cover of X. So if you are willing to have, you need this additional assumption to actually get a correspondence, which is a correspondence of Collet Simpson type, NEX, but G, commutative, locally p-divisible, and also with this funny condition, which are needed in order to see that representations give something in fully faithful way. Okay, if you want to learn more about the proofs, I'm here the full week, but this is all I'm going to say for now. Thank you.
Any questions?
Yeah, Jacob.
Why is f of rho trivial in that example?
Why is f of rho trivial? Because if you, you have to think a little bit about it. But you see that if you factor through this p tilde, if you write it down in SV sheaves, and then you see that the push out will be trivial. I mean, it gives you a section, so to speak. If you write this down properly, you can see that it gives you a section because it factors through that thing. Yeah. I only write it down on points, but you can upgrade this. If you upgrade this to the category where you actually do the push out, you will see that this defines a section. Yeah.
Is there a way to relate this to prismatic F crystals with G structure, maybe explain this correspondence, because I read that there is a relationship between prismatic F crystals and the specialization functor to local systems and to Higgs bundles, and it somehow explains the generalized Simpson correspondence of Faltings. Can one somehow put a G structure on the prismatic F crystals to explain what is happening here?
Yeah, if somebody can do it, it is Johannes Ben and Arthur, are you here? So, yeah, I mean, there's a paper by Anschütz, Heuer, and Lebras about vector bundles, and I cannot say on top of my head if you can do something, but I would be confident. You should talk to them.
Thank you.
Yeah.
So in the complex world, what are the Higgs, I mean, smooth projective, what are the Higgs bundles, the underlying vector bundles of which, trivializes on the limits? I mean, there are the unitary ones, but are there more?
You are talking about the Keller situation.
Well, to find the analogy of
Yeah.
the p-divisible
Yes,
condition.
yes. I mean, I have to think about that. So in the Archimedean world, there is nothing for non-linear algebraic groups, first of all. So this game of the divisibility, I do not know how to play it anyways, because I've never seen anybody working with Torsors on the general Lie groups or something. I mean, that's the first answer. So I've never seen that. And I would guess that you get something more special. But I should say that on the abelian varieties, if we are working over the specific ground field that C is equal to CP, while in the line bundle case, then the old condition, semi-stability, which plays no role, but vanishing Chern classes, is equivalent to the profinite triviality. So,
yeah, but here you can see the analog on the complex side.
yeah, exactly. I can't tell you. I would suspect, but this is just without any knowledge that it's okay, because it for the specific field CP is also okay. Yeah, but definitely one. Yeah, I should check this for GLM. Yeah.
I mean,
This business with the other assumptions on groups is something I don't know any Archimedean analog of.
I mean, on the complex side for rank 1, it is the case that any connection, line bundle comma connection, the line bundle itself is unitary, carries another connection, which is unitary and uniquely defined, and that gives precisely the analogy.
And I would guess for commutative groups, this is always the case. In the non-commutative case, I'm not so sure. Yeah.
Is your assumption you assume constant is locally constant in the?
What do you mean? Do you mean?
Sorry, the theorem, sir.
No, constant. I really mean go through point.
Sorry, I'm asking if locally constant is.
Okay. Yeah, maybe. For me, everything is connected. And I mean really this.
Any other questions? All right. Speaker again.